it's called ecrect R, EQ rect R, and then I want to give it the type family, I think. So the type family will be lambda D vec A D. Yes? So it's abstracting away the thing that has to be equal, and the thing that has to be equal is the dimension. Okay. And what else? Actually I could cheat a little bit. Some of these arguments are implicit. This is what I learned yesterday. So I can check.
A is implicit, X is implicit, P is not implicit.
Okay.
And the rest, I don't know, but you can look it up once you're done.
Okay, so I needed a type family. What's the next one I need to provide?
X.
X. Okay, X is IA3, right? No, it's the n plus 1, right?
Yeah.
Okay, n plus 1. What's the next one I need? The equality already? Is Y implicit?
No, actually, the other way around. The very first thing you need is implicit is the type of n plus 1. Then n plus 1 has to be the next thing before the type family.
I'm not following. I'll read the type again.
So
Okay, I need the type family. Okay, Why doesn't it say here which are implicit and which are not?
You can do about
What? I do about?
EQ rect R.
instead of check.
Better, thank you. See, I'm not a rock expert. Okay. A is implicit, The type family is not implicit, this one we have. And then I need P of X. So I need the vector of size blah blah blah. So this is the concatenated thing that I do have. And it's of size n plus 1. And then I need the equality, right? And that should give us the thing. So I need something of, okay, I'll have a lemma here saying that for all natural numbers n, what do I need? N plus 1 equals
Sn.
n plus 1 equals Sn. Yep. Proof admitted. This is a legit use of admitted. See? And then I can say homework. And this is now foo applied to n, I'm guessing. No?
Need more parentheses.
Attempt to save an...
Parentheses around the ecrect R and...
Yes.
And I think there's the n plus 1 is also.
Yeah, that can go. The n plus 1.
The n plus 1, the n plus 1 is too much. No?
Okay, now foo.
Okay, something else?
So
I think your full limit
yes,
is
it should be
down.
reversed.
Yeah, it's
Oh.
the
So
direction.
yes, if you change the directions, it will work. Yeah, that will work.
That will work?
Yeah.
Yay! Thank you! You did it, I didn't, see? This is my thank you for helping me say this. Okay, so now you see why this is painful. And I already showed you how to do the transfer, so I'm really not going to show you how to post this equation because now you know. But I can share this with you later. Okay. So before I go to the existential quantifiers, I want to tell you about the universe. Okay? So we will... how do I power this off? No, I don't want to power the system. I want to put this up. Does anybody know how to do it? If I can do this. Is it gonna work? Ah, nice try. Thank you. Okay, now I'm doing. So let's see the. Did this work? Not yet. Does this work? Yes. Okay. Let's see the universes, how they are. What they are, how they're defined. And I'm using the book by Petković. So back to the textbook, chapter about the universes. I don't know the number, but I'm going to use the same notation as him. Now, what's the idea behind the universes? The universes are a way for us to express that also the types that we have could be thought of as terms. Okay? The universes are a way to also avoid the Russell's paradox. Okay? So I will just strictly, so there are three things that we want from these universes. One is to avoid the Russell's paradox. The second thing, somebody asked me, like, but we know that 0 doesn't equal to 1, right? And with the universes, we can, actually provide a way to explicitly say that. And the third thing that is useful about the universes is that we can talk about also proof irrelevance in a different way, and I will show you hopefully how Rob does it in the calculus construction. So I'll just start with the definition of what a universe is. So we can think of universes as types that contain types, quote unquote, okay? But actually we don't think of, so this is how we think of them, but formally we cannot really say that. So a universe in type theory is a type U, okay, in the empty context, and it's equipped with a type family T over U. This is type family. And this one is called a universal family. And this type U, we will think of it as the type of codes that represent types. Okay? So the terms of the type U are, codes, and the universal family will map each code to its corresponding type. So we want something further from our universe, and in Martinov type theory, we want this universal family to sort of encapsulate the structure. So we want the pi types and the sigma types and the identity types to sort of not exceed this universe, right? We want to say, if I make a pi type, I still want it to be in this universe. Even if I make a function type, right? I have two types, but the function type I still want to be sort of in this universe. And we express this by the following. So we can say U is closed under pi, and this specifically means that it's equipped with a function, I call it pi, and I don't know what's like a reverse of a hat, like this little V on top. How do you call that in English?
Great.
Caret.
Okay, can you spell that?
C-A-R-E-T.
Isn't it?
What's the other one?
I think it's a hat.
Brave, B-R-E-V-E.
V-R-E-V-E. Brave?
Yeah, search for, yeah, right.
Okay.
That mark is called a hatchet.
Sorry?
Is it called a hatchet?
Oh, I
Yes.
see, yeah.
Yeah. I think that, yeah.
Ah, okay, hat check. Sorry. Hat check. I want to use the same notation as the textbook, that's why I asked. But I can't even pronounce it, so. Okay, such that, so this is a function that takes, so for every x in U, I have a map from T of x to U, okay? So how do I think about this? I think about this as for every dependent type, right? If I write pi, I'm taking a type A and a dependent type family, right? And then I can make a pi type. And this function here will kind of allow me to say, okay, I have a type, and then from a code for a type, and from its actual type, I can make codes for the dependent type, for the B. Okay, so the following equation needs to hold. So I have T of pi with hat check, x, P is judgmentally equal to pi with little x and T of big X, T of P of little x. For every big X in U and big P is a type family T of X. This function. Okay? So this is supposedly telling us how this hat check actually tells you that the universe is closed under the structure of pi. Okay? So if I apply this thing to a code of a type and some type family that is from this type creating new codes, then the code that I'm getting is the pi type. And the correct pi type saying, if I take stuff from this family, from the type that the big X is code of, then I'm getting something in the type that this family, this function P is telling me. Right? So this function P is actually, like I said, if I have, if I think of this here as type A, so this is a family, this is a function that from A it produces codes for B. Because of every X, every little X in A, I need B of X, and this family is for every X in A producing me a code that will represent B of X. Okay, so if I decode this, so you see this pi hat check is landing in U, so it's a code for a pi type, right? And the interpretation, the type, the actual type that this is coding is the actual pi type, right? That respects the structure. Question? Yes.
Do you have an example?
No. I know this is very abstract. I mean, we could try with like concrete examples, right? If I have a code for, we can try with a concrete example, okay? So we also know, so I wanted to continue this definition, but maybe this is more useful, right? I will also have codes, so I'll have T of the code for the empty type, so I will call it empty hat check, which will be definitionally equal to the empty type. I'll have the code for one hat check. This is the unit type, and it's going to be the unit type. And I also have the code for the natural numbers type, and it will be judgmentally equal to the natural numbers. Okay? So now if I have this, let's try it with some codes. Okay? So let's see. I can apply phi hat check to, so I need a dependent, so I need a function, right, that will give me a proper type family, right? So let's say, okay, for my P, I could take, sorry? Okay, let's do something that I already have a code for, right? So let's try with something like this. I could say from natural numbers to I'll make a constant function. So for every natural number, I'm giving myself a type of natural numbers, okay? So this would be like a dependent type family where x is a natural number, and this is n type. I know it's boring. Okay, we can do also something in C level. We can have not the natural numbers, but we can have the empty type, okay? So here, this is like for every x in natural numbers, I'm giving myself an empty type. Now I can what I'm trying to do here is, okay, my x now is the code for this type here. So x, big X here is going to be the natural numbers hat-check type. Okay? So what I'm saying here is if I have I hat-check on natural numbers type natural numbers type hat-check, and I give it a P, so this P here. Okay, this is a really bad example because I want the actual. I'm going back to the natural numbers. Okay, so I have this, and then I get P. This is fundamentally equal to having a pi, where I take little x in natural numbers, and I have P of x. Okay? And now I can compute this detrimentally equal to x in n, it's pi, and then tau of P of x. We know that every x is going to be this one, so it's tau of natural numbers code, and this is differentially equal to pi. I have x in n, natural numbers. Who understands this example? Nobody. Good. Question.
I don't know if this is a valid question, but is it possible that this could be like some fixed point in x? Like is the bottom, is it expressing some sort of fixed point?
Where am I expressing a fixed point?
Like I don't know. Sorry, never mind.
Okay, sorry.
I mean, so I don't know if this is the correct conclusion, but it feels like it's possible that, you know, like there's some x, and you're saying that, like, closure sometimes feels like a fixed point because you sort of keep applying to yourself. I don't know if I'm interpreting it right, so that's why I said I'm not sure if it's valid. But.
So fixed point means that I'm sort of recursively calling something.
Yes.
What am I recursively calling?
I'm trying to say, like, maybe the equation at the very bottom can be interpreted as like some, like you're saying something is the least fixed point to this equation, but I don't know if that's true.
No, I'm not saying it's the least fixed point. I'm proposing this exact equation.
Oh, wait, thanks.
Yes.
All right.
Okay. Who wants to? Oh, yeah.
I wanted to ask a two-part question, and they're related. And this may not make sense, but what is the cardinality of U? And what would you admit in code, just so I can understand it better? Could I choose
cardinality of U. I will hopefully explain it a little bit, how we generate. So it depends on the universe level, okay, which we will get to. So the very base case, it will be just the code for natural numbers, unit type, empty type, the code for hat check, pi, hat check sigma, and hat check identity type. And then however we can combine them in this sense. So it's really defined, okay? And then all of the next levels, I will show how we get them in a little bit, if that's helpful.
My main question was, I wanted to understand the structure of the code for those that have to check.
Yes. So it's, for now, it's just, a symbol, a code for, so the structure is like this. I'm giving myself a symbol, empty hat check, so it's just a symbol, and this symbol represents the code for the actual empty type.
It's going to be part of the index.
Yes. It can be taught, I think of it as a point, like one constant point in a set, in a type called U.
So that's why I was asking if I could choose numbers for that index if I was implementing this.
Well,
And this is Tarski, right?
yes,
Okay.
this is Tarski encoding of the universes. Question?
So when you tell me that U is supposed to under pi, what I hear in this room is like, okay, if some type is in U, then a pi that takes that type will also be in U.
Yes.
I'm having trouble connecting that idea with what's on the board. I'm understanding why we need like the new symbols as a thing to make it close under pi.
Okay. So I'm saying that U is the type of code for the things.
Oh, so
Right.
U is not the type of types, it's the type of codes of types?
Yes. Does that make it better?
I think that makes it better.
Because I don't want to say that types themselves are terms in something called U. This is weird, okay? I mean, people do say that, right? People will simplify all this and just say, oh, well, actually, these types are just the terms in the next universe, or the terms in this universe. But actually, formally, they're not. The universe is a type of codes for types, and then the universal family is the decoding function that takes the code for a type and gives you the actual type.
So how of X is going to take you from a code to a code, or it's going to take you from a code to is X
Okay? Tau of the code for unit type is the actual unit type. Okay? So these hat check things are codes. Okay, I'm using hat check because I want to say this is not actually the entire type, but I want to know which type I'm referring to, so that's why I'm using hat check, right? So these are codes, these are like points, these are elements of, these are terms in type U, okay? So your hat check is in U, one hat check is in U, and hat check is in U, but N is not in U.
Okay.
Tau of N, T of N is in U.
Okay.
Does that make it better for the rest of you as well? Who gets it now? 3 people, yes, or more.
I have a question.
Yes, question.
So is tau in U? Is the universe level of tau also in U? Or does it, is it not a type?
Tau is,
Yeah, the type of
tau
tau.
is the universal family.
Oh, so there's no notion of like the type of tau being in U or something. Oh.
I have 2 questions. One, so is the input to tau is a code?
The input to tau is a code.
And then is the output of tau also a code?
The output of tau is the actual type.
But why then is why is tau in there in U? Because isn't U the universe
Ah.
of codes?
Okay. Probably I said something stupid. Okay, let's see it again. I wanted to say, yeah, that the natural numbers in U is not okay, right? That's not true. It's a type. Okay? And the natural numbers is the tau of the code of Hatzek. Okay. Thank you.
I'm confused again, because if the natural numbers are the tau of the code for the natural numbers, then how come we can have the natural numbers turn into, is that pi over there that takes tau of x and takes us to u, is that taking us from a symbol to the type, to the symbol again? Or?
Are you talking about this?
Yes.
Yes. Particular this between these two parentheses.
Within those two parentheses, yes, that's
Yes.
taking us from a code to a type to a code.
So this here between the parentheses, okay, is this is an actual type.
Okay.
So imagine natural numbers here,
Okay.
okay? And for each natural number, I'm giving a code,
Okay.
okay? So this is from an actual type. So this is a function from type to type, right? This type is a concrete thing that was encoded by X. This type is the U. I'm saying U is a type.
Okay.
Okay, so this is the actual function between type tau of X and type of U.
Okay.
More questions?
I've seen this presented before, like without this encoding.
Yes.
What is the difference, or like why?
Okay, what's the difference?
Or one, like, is there a reason to prefer one or the other? Or
Okay.
what's the
This is formally okay. This is, telling you exactly what it is. And the other one is pretending that it is what it is, but it's actually this under the hood.
But is there underlying meta-theoretical reason why it has to be like this? Or is this just the way that it's presented
So,
and it's informal?
Yes. Types are not terms. This is the meta-theoretical reason.
But
For my definition of a type theory, types are not terms. So types cannot be in a type. Terms can be in a type.
So is that just the particular way the system is defined? Or
Yes,
is that
this is how I define the type
Yeah, I
theory.
know, but I'm saying would it be invalid, would the system not be consistent? Would something break down and be defined differently, or is this just a particular fact? Or is it necessarily for some reason it would break down if you didn't do it that way?
So even if I try to do it the other way, types can be just terms in another universe, right? Under the hood, I would still actually, pretend that this, what I call type here, is a term in the next universe, but then it's actually like having a term which is a code for the thing. So I think this is cleaner. But how people usually think about it. So this is formally how it is. And then if you try to do the other thing, then you run into trouble of explaining what exactly, how can you manipulate then these terms and types, right? Because if I say n hatcheck is a code, then you're not pretending you know what the elements of n hatcheck are. This is just a term of type U. But if I tell you I have a natural numbers type, then then you can start writing things like I have a natural number n, in type U, and then what is this? So what you really mean when you write this thing, and sometimes you just want to pretend that it's true, right? You just want to pretend that it's actually in time, right? But to make it work under the hood, you're actually saying, well, actually, this U doesn't know about this little n directly. It knows about this little n through a decoding function. Okay. Question?
For the middle line right there on the right of the board, should there be a tau wrapped around the first term before the governmental equality?
Where did I mess up now?
It's like on the right side, on the right half, and the first term
Here.
of this line. Before that.
Here.
Yeah. Should there be a tau wrapped around this thing?
Yes.
Okay.
Thank you. Yes.
I think I asked about this earlier, but I didn't understand. Is there like a way to talk about the output of this tau function?
A way to
Because-
talk about the output of tau.
Because it's giving you back like types,
Yes.
but we're not collecting these into a universe. Do we? I
So
guess why
tau
don't
is
we
taking
collect
the
them?
code for the type and is giving me the actual type.
Okay.
Yes. So this is a type.
Mhm.
Tau of x is an actual type. I can write tau of x type. And I can write u as a type. And I can write n is a type. But I can write n hat check is a term of type u.
Oh, I think the question was, what is the type of tau? Like, does it can't return u, right? Because u is the type of codes.
Do you ever
So-
talk about like
Yes.
Right, I think, okay.
if you're not calling it a type, some
And I explicitly don't want to write this.
Okay.
okay.
Tau is a type family. Okay? What I can write is for every little x in U, tau of x type.
Oh, right, okay.
I'm postulating this judgment. Okay, and then I'm postulating more computation rules saying that tau of natural numbers hat check is judgmentally equal to natural numbers in the empty context.
And is like the vague intuition behind this that you don't want to mix terms and types here?
Is there an intuition to get this if you don't want to get stuck into what? I didn't-
It's like the vague idea that you have this distinction between like n hot check and n because you don't want to mix terms and types?
Yes,
Okay. Okay.
yes.
Thank you.
Is the motivation for that distinction to avoid predictivity? Like, I would call it type, and this is in particular.
Yes.
And then my other question is,
But then prop will violate that, so good luck.
because a lot of the books that I've read, they go, I think it's Russell, the Russell.
The Russell paradox?
Well, not that, but they define it as, as I understand, there are two ways to do